So welcome to the second lecture of the third week of Lent term. And last time we introduced this notion of cardinality of an infinite set. We say that an infinite set is countable if there exists a bijection from the set of natural numbers to this set. And it's said to be uncountable if there does not exist any bijection from the set of natural numbers to this set. And last time we saw that the set of natural numbers and the set of integers is countable, and today we will start by showing that the set of rational numbers is also countable. Later today we will also see that the set of real numbers is uncountable, and in fact if we take any open interval a comma b where a is strictly less than b, then this set is also uncountable. We'll also see that the set of irrational numbers is uncountable, and the uncountability of the set of real numbers will be proved using the fact that if you look at the set of all sequences, each term of which is either 0 or 1, okay, then the set of all these sequences is uncountable. So we'll first prove that, and using that we'll show that the set of real numbers is uncountable, from which these other things will also follow. But before showing that this set of rational numbers is countable, we'll begin by proving some useful results about countable sets. So we'll show that every infinite subset of a countable set is countable. So if you have a countable set and you take any infinite subset of this countable set, then that's also countable. And also we'll show that if A and B are countable, then the Cartesian product of these two sets is also countable. We also remark that we said that a set is countable if there exists a bijection, let's call it F, from n to s, but that's the same as saying that there exists a bijection from s to n, because when you have a bijection from n to s, the inverse of that will also be a bijection, and that bijection will go from s to n. Vice versa, if you have a bijection from s to n, then the inverse of that bijection will also be a bijection, and that bijection will go from n to s. Okay, so let us now show the theorem which says that every infinite subset of a countable set is countable. So we have been given a countable set and an infinite subset of that countable set, and we want to show that that infinite subset is in fact countable. So let us prove this first in the case when the given countable set is in fact the set of natural numbers, and let us suppose that we have an infinite subset S of this set of natural numbers, and we want to show that this infinite set is in fact countable. So we want a bijection, let's call it F, from the set of natural numbers to S. Now the idea of the construction of this bijection is very easy. We will first construct a sequence an indexed by n, and then we will simply take f to be the map which sends n to an, and this sequence is constructed as follows. So imagine that you have the natural numbers here, and the elements of s of this infinite set are marked in red. Okay, so maybe 4 is there, 5 is there, 7 is there in this s, 9, and so on. It goes on forever because this is an infinite set. Then as a1, you simply take the minimum of all of these red points, so that will be 4. So in this particular case, and so this function f will map 1 to 4, that will be the first element. Then you remove 4 from this infinite set and look at the remaining red points, and the second element is taken as the minimum of that resulting set, which happens to be this 5. Then you remove 4 and 5 from this set and look at the remaining red points, and the third element will be the minimum of that, so that will be the 7. Then you remove 4, 5 and 7, and in the remaining set take the minimum, so that's 9, that will be the fourth one, and so on. So this sequence is constructed recursively. A1 is just the minimum of the points of S, and if A1 to AK have been constructed, then AK plus 1 is simply the minimum of this set, where from the set S you remove A1 to AK, and whatever is left you take the minimum of that. Well, the first question is, does this minimum exist? And the answer is yes, because this is a non-empty set, because this set S is infinite and you're just removing finitely many points. So what is left is still an infinite set, so it's certainly non-empty. Moreover, it's a collection of natural numbers, and so by the well-ordering principle, this minimum does exist, and that's this AK plus 1. So knowing A1 to AK, we know how to construct AK plus 1, and so we have got this sequence in this manner. And let us now prove the claim that AK is strictly less than AK plus 1 for all k which are natural numbers. So this means that the sequence is strictly increasing, and this will help us to prove that this f is injective. Okay, so let us first suppose that k is bigger than 1. Okay, and let's first show that ak plus 1 is bigger than or equal to ak, and then we'll also show that ak plus 1 is not equal to ak, and this will show that in fact ak plus 1 is strictly bigger than ak. Okay, now what is this ak plus 1? That's the minimum of this set, where from the set S you remove a1 to ak. And what's ak? Similarly, from the set S you remove a1 to ak minus 1 and take the minimum of that. Now we also note that from the set S, if you remove a1 to ak, the resulting set is a subset of the set you obtain when from S you remove a1 to ak minus 1, because over here you are removing more elements, so of course you get a smaller set. Now this minimum of this set, okay, which is this quantity, is smaller than each of the elements of this set, and this being a subset, this is also smaller than each of the elements of this set. So this thing is a lower bound for this set, but this was the greatest lower bound of this set, so this is of course bigger than or equal to any lower bound, in particular this one. So you have got that this is bigger than or equal to this. In other words, ak plus 1 is bigger than or equal to ak. Now ak plus 1 is the minimum of this set, so it belongs to the set, being the minimum. So this belongs to this set. So ak plus 1 is in S but is not any of a1 to ak. In particular, it is not ak. So ak plus 1 is not ak, and it's also bigger than or equal to this one, so it has got to be strictly bigger. And what about when k is equal to 1? Well, it's a similar proof. So a2 is the minimum of S other than a1. So being the minimum, it belongs to this set. So a2 is certainly not a1, because it is in S but it is not equal to a1. And a1 is the minimum of S, and that's less than or equal to this minimum of S minus a1 by a similar argument as over here. And this is our a2. So a1 is less than or equal to a2, but a2 is not equal to a1, so a1 has to be strictly less than a2. Okay, so you have got that ak plus 1 is bigger than ak, which in turn is bigger than ak minus 1, and all the way it goes down to a1. So this is an increasing sequence that we have constructed. So now the function f is simply the one which sends the natural number n to an, and then it's clear that this is injective, because if you have two distinct elements from over here, well, since they are distinct, they will be unequal, so one will be smaller, the other will be bigger. So let's label them as little n and capital N. So we know that little n is strictly less than capital N. But then, since this is an increasing sequence, an is strictly less than a capital N, but then an is not equal to a capital N. And so the images of these distinct points are distinct, and so the function is injective. Okay, so now let us show also that this map is surjective, so that it will be a bijection, and that will show that this S is countable. We want to show that this F is surjective, so given any element of S, we should show that it's F of something. So let M be an element of S, and the task is to show that this M is F of something, okay, some natural number. We first claim that it is not the case that Fn is a subset of the set containing 1 to m. Okay, because if Fn was a subset of this one, then in particular F1 to Fm plus 1, these m plus 1 points would belong to this set containing 1 to m. Okay, so you are putting these numbers in these m boxes, but then since there are m plus 1 of them, by the pigeonhole principle, 2 of them will have to fall in the same box. So there are two numbers n and n prime amongst 1 to m plus 1, such that Fn equal to Fn prime, but that contradicts injectivity, and so this cannot happen. So that means that there must be some natural number such that Fn exceeds this m, so Fn is strictly bigger than m. Okay, so now if I look at the set of all n such that Fn is bigger than or equal to m, then that set is not empty, because we know that there exist n's for which Fn is strictly bigger than m, in particular bigger than or equal to m. So this is a non-empty set of natural numbers, and so by the well ordering principle, the minimum of this set exists. Let's call that n star. Now what we know is that this n star belongs to this set, and in particular Fn star is then bigger than or equal to m, so we already know this. And we also know that F1 up till Fn star minus 1 has to be strictly less than m, because if it was greater than or equal to, then you would have that this minimum is even smaller than n star. Okay, so all of these are strictly less than m. So none of these can be equal to m, right? So m is not equal to f1, it's not equal to fn star minus 1. Okay, and hence it does not belong to this set. Now let us show that fn star is less than or equal to m, and then these two put together will give that m is f of n star. So we are now proving this. We already know this, and we are now proving that fn star is less than or equal to m. So fn star is equal to an star by definition, and an star by definition is the minimum of this set s minus a1 to an star minus 1. But this a1 is f1, an star minus 1 is fn star minus 1. Okay, so this minimum is just this minimum. Now let's note that this m belongs to this set. That's what we started off with. We are taking something in here, and m does not belong to this set. That also we concluded from over here, right? So this m belongs to this and it does not belong to this set. So it belongs to this set other than f1 to fn star minus 1, right? And then we are taking this minimum. Okay, and the minimum is smaller than all the elements of this set, but m is an element of the set, so this minimum is less than or equal to m. So we have also proved this. Now these two put together imply that fn star is equal to m. This finishes the proof of the claim that this is surjective. Now we had already shown that this map is injective. Now since this map is surjective and injective, it is bijective, and this shows that S is countable. So far what we have got is that if you started with the set of natural numbers and you took any infinite subset of that, then that infinite subset is countable. But the claim was about any countable set, not just the set of natural numbers. So now let us handle that case. So we now consider the general case where T is any countable set and we have an infinite subset S of this countable set. And so far we have considered the case when this T was the set of natural numbers, but now this is any arbitrary countable set. And we want to show that this S is countable. Now since this set T is countable, we know that there is a bijection, let's call it G, from N to T. And then we also have a bijection G inverse from T to N. And instead of writing inverse all the time, let's call it phi. Okay, so we have a bijection phi from this set T to the set of natural numbers. So here is sort of a schematic diagram. Here is T, here is the set of natural numbers, and here is the map phi. And this set S is a subset of this set T, and we can look at the restriction of this phi to this set S. Okay, so that I label by phi restricted to this set S, and we can look at the image of this set S under this restriction map. Okay, so that's what I call the set phi S. So that's the image of S under this map. It's the range or the image of this function phi restricted to S. So this phi restricted to S goes from S to phi S, and it is a surjective map because everything in here comes from something over here, and it's also injective because if you had two distinct points over here, the image under the restriction of phi to S is simply the image under the old map. Okay, and since the old map was a bijection, in particular it was an injection, so distinct points will be mapped to distinct points over here. And so in fact this restriction map is also injective. So this phi restricted to S going from S to its image is a bijection, and since S is infinite, it then follows that its image is also infinite, because if its image was finite, then by the pigeonhole principle, since this set is infinite, two of them will be forced to go to the same point, which will violate the injectivity of this map. So it follows from the facts that this map is injective and this set is infinite, that also this phi S is infinite. Alright, so we now have this phi S, which is a subset of N, and it's an infinite subset of N. And this implies, by what we have just proved, that this is countable. So since it's countable, there exists a bijection from N to this set phi S. And then if I look at the inverse of that, then we have a bijection also from phi S to N. But we also know that we have a bijection from S to phi S, that was this restriction map. So this is a bijection, this is a bijection, so their composition is also bijection. So we have got a bijection from S to the set of natural numbers. and the inverse of this is also bijection, and this time from n to s. So we have got a bijection from n to s, and that shows that this set S is countable. So we have just proved that every infinite subset of a countable set is countable. Now we know that the set of natural numbers is countable, so if I take any infinite subset of that, then it will be a countable set. For example, if I take the infinite set comprising all the squares, that's a countable set. And if I take the infinite set comprising all the prime numbers, then that's also a countable set. We have also seen last time that the set of integers is a countable set. And now if I take all the even integers, that is integers of the form 2 times m, where m is an integer, that set is also a countable set because it's an infinite set and it's a subset of this countable set. We will now show the theorem that if A and B are countable sets, then the Cartesian product of A with B is also countable. So this is the set of all ordered pairs where the first component of this ordered pair comes from the set A and the second component of the ordered pair comes from the set B. Alright, so here is the proof. We know that the set A is countable, and so there exists a bijection, let's call it F, from the set of natural numbers to A. So then this map is surjective. So this A is the image or the range of this function. So this A is the set of all Fn where n is a natural number. So it's the set F1, F2, F3 and so on. Now if I call this F1 as A1 and F2 as A2 and so on, in general Fn is An, then this A is the set An where n is a natural number. Similarly, since the set B is countable, there exists some bijection, let's call it G, from the set of natural numbers to B, and let's call the images of the natural numbers under this G as B1, B2, B3 and so on. So again we have that since this map is surjective, this B is the image of this map or the range of this map, and that is equal to the set containing B1, B2, B3 and so on. So the Cartesian product of A and B is the set of all ordered pairs where the first entry comes from A and the second entry comes from B. But we know that this set A is really the set A1, A2, A3 and so on. And the set B is really B1, B2, B3 and so on. And so A Cartesian product with B is really the set of all ordered pairs AM, Bn where M and N are natural numbers. So it's the set A1, B1, A1, B2, A1, B3 and so on. Then A2B1, A2B2, A2B3 and so on, then A3B1, A3B2, A3B3 and so on, and continue in this way. So we have arranged the elements of this set so that over here in this first row, the first component is always A1. In this second row, the first component is always A2. In this third row, the first component is always A3 and so on. Now we want to show that this A times B is countable. And so we want a map which is a bijection from the set of natural numbers to A times B. Alright, so we produce the map in this way. Basically we have to list these elements and we do it in this manner. We start with this element that we take as h of 1, then this is h of 2, this is h of 3, this is h of 4, h of 5, h of 6, and we continue going in this zigzag way. This map is surjective because if I take any element in here, that will be in this array, and by continuing in this zigzag way, eventually this blue curve will hit that element. And moreover, it is also clear that it is injective because once we pass an element, we never return to it because we go to a subdiagonal, right? And we continue going farther and farther. And along a sort of diagonal, we just cover the elements once. So we never repeat there either. So it is also clear that it is injective. Now, this was a very visual sort of proof, but in the exercises, there is an alternative proof which is less visual, but sort of more concrete. And a corollary of this is that, well, since Z is countable, the Cartesian product of Z with itself is also countable. And we'll use this to show that the set of rational numbers is countable. So that's the next task. We are now ready to prove the theorem that Q is countable, the set of rational numbers is countable. Now first of all, if you have a rational number, we can express it in the form n by d, where n and d are integers and d is positive. But this Q is really an equivalence class, So there can be lots of ordered pairs n comma d in this equivalence class where the d is positive. But all these positive d's, they are really natural numbers. Okay, and by the well ordering principle, you can take the smallest possible such d and let us call it d star of q. And the corresponding numerator, whatever it is, let's call it n star q. In other words, q is equal to n star q by d star q, where this denominator is the smallest possible natural number. Now we define a map f from q to the Cartesian product of z with itself as follows. If you have this q, you can express it as n star q by d star q, where this denominator is the smallest possible natural number, and you simply map this q to this ordered pair n star q comma d star q, each of which is an integer. Now I claim that this f is injective. So let us suppose that q and q prime are two rational numbers, okay, and let us suppose that f of q is equal to f of q prime. Now what is f of q? That is simply the ordered pair n star q comma d star q, where q is equal to n star q by d star q. And what is f of q prime? That's n star q prime comma d star q prime, where q prime is equal to n star q prime by d star q prime. And we know that these two are the same, so that means that these two ordered pairs are the same. So we know that n star q is equal to n star q prime and d star q is equal to d star q prime. So it follows that n star q by d star q is equal to n star q prime by d star q prime. But this is q and this is q prime, so we have got that q is equal to q prime. So if f of q is equal to f of q prime, we have shown that q is equal to q prime. In other words, this f is injective. So this f goes from q and the codomain is z times z. But suppose we restrict the codomain to exactly the range of this mapping. So then we get a new mapping which goes from q to the range of this function or the image of this function, and that we denote by fq. And then this mapping, which we again denote by f, slight abuse of notation, is now surjective because everything in here is f of some rational number. Okay, so it is surjective and it's also injective because that we had checked. So this is a bijection. Now, since it is in particular injective and since this q is infinite, it follows that fq is also infinite, because otherwise, if it was finite, then the images of this infinitely many rational numbers would all have to go in that finite set, which is this range, but then by the pigeonhole principle, two of them would have to be the same. And that will mean that this map is not injective, but we have already seen that this map is injective. So this shows that this range is in fact infinite, but this range is a subset of z times z, which we know is countable. And since we have an infinite subset of a countable set, this itself is countable. So that means that there exists a mapping which is a bijection from n to fq, and the inverse of that mapping will then be a mapping, let's call it g, from fq to n. So we have got a bijection from fq to n. Meanwhile, we also had this bijection from q to fq. And if I compose these two bijections, then I get a bijection from q to n. And the inverse of this bijection from q to n will be a bijection from n to q, okay? And that shows that q is countable because we have a bijection from n to q, okay? So this completes the proof that the set of rational numbers is countable. So far we have seen several examples of countable sets, the set of natural numbers, the set of integers, and the set of rationals. But so far we have not seen a single example of an uncountable set. So here is a first example of an uncountable set. We will look at the set of all sequences which are 0 or 1 valued. So this is really the set of all functions from n to 0, 1. Okay, so it's a whole lot of functions. All the functions from n to the set containing 0, 1, you put in a set, and that's this set S, and we'll show that that is uncountable. This might seem like a strange example to consider, but we'll soon use this to show that the set of real numbers is uncountable. Let us suppose, on the contrary, that this set is countable. So that means that there is a bijection, let's call it phi, from the set of natural numbers to S. Now, since this is a bijection, in particular it's a surjection. So this S is the image of this map. Okay, so this S is the set of all phi n's, where n is a natural number. So it's the set phi 1, phi 2, phi 3, and so on. So all of these are functions. So let's call phi1 the function f1, that's a function from n to 0, 1. Let's call the function phi2 as f2, so that's a function from n to 0, 1. The function phi3 I call f3, and that's a function from n to 0, 1, and so on. Now the idea of the proof is that we'll arrive at a contradiction by constructing a function from n to 0, 1 which belongs to this set, but it is not the phi of anything. Okay. Now for it to be the phi of something, it should be either f1 or f2 or f3 or some fk, but we'll show that it cannot be any of these. Okay. And the way we'll do this is we will have this new function differ from f1 at 1. The function f is such that it differs from f2 at the value 2, it differs from f3 at the value 3, and so on. Okay, so let's look at what the range of this f1 is. It has the values f1 at 1, f1 at 2, f1 at 3, and so on. The range of f2 likewise is f2 at 1, f2 at 2, f3 at 3, and so on. And the range of f3 is f3 at 1, f3 at 2, f3 at 3, and so on. Okay, so now our f of n will be such that when n is equal to 1, it differs from this one. So note that each of these functions are 0, 1 valued, so this can be either 0 or 1, this can be either 0 or 1, this can be either 0 or 1, and so on. So if this is 0, then you take f at 1 to be equal to 1, and if this happens to be 1, then you take f at 1 to be equal to 0. Okay. Similarly, whatever this value is, you toggle that value and take that as f of 2. So then this f will be different than f2 also, because its value at 2 is different from the value of f2 at 2. And similarly, whatever this value is, you take f at 3 to be other than this value. So if this is 0, you take it 1. If this is 1, you take it 0. Okay. So the definition of the function now is like this. So f is a function from n to 0, 1, which is defined as follows. The value at fn, to decide its value, you just look at fn at n. If that happens to be 1, you take fn to be equal to 0, and if fn at n happens to be 0, you take f at n to be equal to 1. Okay, so you basically toggle the value. So first of all, we note that this f is an element of this set. It is indeed a function from n to 0, 1. But let's show that this f cannot be any fk. You see, first of all, f is not f1 because the value of f at 1 is not f1 at 1. Similarly, f is not f2 because the value at 2 is not f2 at 2. It is not f3 because the value of f at 3 is not f3 at 3, and so on. Right? So this function differs from f1 at 1, differs from f2 at 2, differs from f3 at 3, and in general it will differ from fk at k. So if this f were in this set, so it would be phi of some k, so it would be fk, but f is not fk because the value of f at k is not equal to the value of fk at k. Right? So this shows that this f is a function in here, but it is not phi of anything because then it would be some fk, but it's not, and so this phi is not surjective, which is a contradiction to the fact that this phi was a bijection and in particular surjective. So this contradiction shows that our original assumption that S is countable cannot be true. So this set is uncountable. Now let us see how we can use this to show that the set of all real numbers is uncountable. We will now show that the set of real numbers is uncountable. So we already know that if you look at this set S, which is the set of all functions from n to 0, 1, that set is uncountable, and we'll use this to show that R is uncountable. Now the plan is like this. We'll first construct an injective function from this set S to the set of real numbers. Then we can look at the image of this function phi, and let's call that as phi s. So then if I look at this same mapping but with this codomain a possibly smaller set, which is this phi s, then this new map, which we denote with the same symbol, is a surjective map because everything in here is phi of something, and moreover it is injective because the original map was injective. So this new function with this new codomain is a bijective map. Now we also know that this set is infinite because S is of course an infinite set, and this phi is an injective mapping. So that shows that this phi S is infinite too. And the reason is because, again, because of the pigeonhole principle. Because if it was the case that this was a finite set, then since this is an infinite set, then there must be 2 points in here whose image is the same, but that contradicts the injectivity of this phi. So this phi s is infinite, and we also know that this phi s, which is the range of this function phi, is a subset of R. So you have an infinite subset of R. Now if R is countable, then since this is an infinite subset of a countable set, this would be countable. Okay, so that would mean that there is a bijection from N to this phi s. And then the inverse of this mapping would be a bijection from phi s to N. In the meantime, we also have this original bijection from S to phi s, which is this phi. Okay, so that's also a bijection. And if I compose these two bijections, then I would get a bijection from S to N. But then the inverse of this bijection from S to N would be a bijection from N to S. And so this would mean that S is countable, but we have just seen that this set S is uncountable. So that's a contradiction. And this contradiction will show that it cannot be the case that R is countable, and so R has to be uncountable. So to carry out this plan, the only thing that we have to do is to produce such an injective mapping from S to R. So we want a mapping phi from S to R which is injective, and this mapping will send any element of S, which is actually a function from N to 0, 1, it should send it to a real number. Well, we will construct the function in this way. Once you have this function, then you can construct a sequence from that function as follows. As the nth term of this sequence, you take this partial sum, f1 by 3 all the way up till fn by 3 to the power n. Okay? And we will soon see that this sequence, which is constructed from this function f, is in fact a convergent sequence. Since it is convergent, it will have a real limit, and whatever that real number limit is, that you associate with this f. So f in S is sent first of all to this sequence, which we'll soon see is a convergent sequence, and so it will have a limit, and whatever that limit is, that will be phi of f. Okay, and we'll soon see that this function phi is also injective. But the first task at hand is to explain why this sequence is convergent. Now, long ago in the Michaelmas term, we had learned that if a sequence is bounded and monotone, then it's convergent. Well, we'll show that this sequence is increasing, so it's monotone, and it's also bounded. To see that it's increasing is very easy, because if I look at the n plus first term and subtract the nth term, well, all that will be left is fn plus 1 divided by 3 to the power n plus 1. And let's recall that f is a function in S, so it is 0, 1 valued. So fn plus 1 is either 0 or 1. Well, it's non-negative in any case, and so this is bigger than or equal to 0. So you have that an plus 1 is bigger than or equal to an for all n, and so this sequence is increasing. Now let's also show that it's bounded. Well, the nth term is given like this, and we know that each of these numerators is either 0 or 1. So let's overestimate it by 1, and then this is less than or equal to 1 by 3 all the way up till plus 1 by 3 to the power n. These summands are in geometric progression, and then by multiplying and dividing by 1 minus 1 by 3, we know that, well, this turns out to be 1 divided by 3 times 1 minus, there are n terms, so 1 minus 1 by 3 to the power n divided by 1 minus the common ratio, which is 1 by 3. Now 1 minus 1 by 3 is 2 by 3, and this numerator is strictly less than 1. So this is less than 1/3 times 1 by 2 by 3, the 3 cancels, leaving a half. So each term of the sequence is less than or equal to a half, and so this sequence is bounded. This sequence is bounded. So since it's monotone and bounded, it is convergent, and whatever the limit is, that will be phi of f. Now it remains to be shown that this phi is injective, because once it's injective, then we can give this argument to show that R is uncountable. Okay, so let's now see why phi is injective. So our claim is that phi is injective. Let's recall that this phi is the map which sends elements of S to R. Elements of S are these functions from n to 0, 1. And then we know that we can construct that sequence which is convergent, and it has a limit, and whatever that limit is a real number. So phi of f is whatever this limit is. Now I want to show that this mapping, which sends functions to these numbers, that map is injective. So let us suppose that there are two elements in here, which are functions f and g, which are distinct elements of this set, such that their images are the same, and we'll soon arrive at a contradiction, showing that that can't happen, so the function phi is injective. Alright, so what does it mean that f and g are distinct elements? Well, f and g are functions from n to 0, 1, so they are distinct functions. So it cannot be the case that for all n, fn is equal to gn. Okay, so there must be some n where f of that n is not equal to g of n. And let's take the smallest such possible natural number and let's call it n star. So we know that there exists a smallest n star, a natural number, such that f of n star is not equal to g of n star. That means that, well, one is bigger than the other. Let's suppose, without loss of generality, that f of n star is strictly bigger than g of n star. And if it's the other way around, we simply relabel the two functions. Alright, now since these are 0, 1 valued, that means that this has to be 1 and this has to be 0. So then we also know that f of n star minus 1 is equal to g of n star minus 1, because this was the first n where the two functions are different, all the way down to f of 1 is equal to g of 1. Now let us define sigma, a number, to be equal to f1 by 3 plus so on up till f of n star minus 1 by 3 to the power n star minus 1, but we know that this thing is the same as g of n star minus 1, right, because this was the smallest n star where the two functions take different values, and similarly g of 1 is equal to f of 1. And of course it might be that n star is equal to 1, in which case we take sigma equal to 0. Okay, and otherwise if n star is strictly bigger than 1, then we define it to be this quantity, which happens to be the same as this quantity, because of our observation that this is the same as this and this is the same as this. So for every n which is strictly bigger than n star, let's look at f1 by 3 all the way up till fn by 3 to the power n. Well, since n is strictly bigger than n star, somewhere down the line you will have fn star divided by 3 to the power n star appearing, and then it will continue f of n star plus 1 by 3 n star plus 1 all the way up till this thing. Now over here we see that this summand will appear, so this is bigger than or equal to sigma, and then f of n star we know is equal to 1, so this can be replaced by 1, and then you have some non-negative terms, so I underestimate it by 0. So this is always bigger than or equal to sigma plus 1 by 3 to the power n star. Now this is true for every n which is bigger than n star. So if I pass to the limit as n tends to infinity, we will have that the limit of this as n tends to infinity is bigger than or equal to the limit of this as n tends to infinity. So but the limit of this as n tends to infinity is exactly phi f, and this is just a constant sequence, does not depend on n at all, and so this is just sigma plus 1 by 3 to the power n star. So we have got this inequality. Okay, and we also have that if I have n bigger than n star, if I look at the corresponding sum but with g instead of the f, then you have this thing which is less than or equal to, well, I recognize this part appearing here, which is this sigma, then g of n star we know is equal to 0, and then all of these numerators are either 0 or 1, so they are all less than or equal to 1. So this is less than or equal to 1 by 3 to the power n star plus 1 all the way up till 1 by 3 to the power n. Now summands over here are in geometric progression, so we know the sum of this, that is 1 by 3 n star plus 1, 1 minus 1 by, how many terms are there? Well, this starts n star plus 1, and then this n I can write as n star plus n minus n star, so there are n minus n star terms, and then the common ratio is 1 by 3, so I have 1 minus 1 by 3 in the denominator. Okay, now this thing is less than or equal to 1, and so I overestimated by 1, divided by this happens to be 2 by 3. So one of the three cancels against this, leaving this quantity over here. So again, if I pass the limit as n tends to infinity, then this one will be phi g, and that's less than or equal to the limit as n tends to infinity of this one, but being a constant sequence, the limit is just sigma plus 1 by 2 times 3 to the power n star. So I've got this highlighted thing and this highlighted thing. So let's see what we can do if I put these two together. So phi of f is bigger than or equal to sigma plus 1 by 3n star, and that is of course strictly bigger than sigma plus 1 by 2 times 3n star, right? Because this denominator is bigger, so the number obtained is smaller. Yeah, so that's why there is this strict inequality. And this thing we know is bigger than or equal to phi g. So we have got that phi f is strictly bigger than phi g. In particular, phi f cannot be equal to phi g, and that's a contradiction over here. So you cannot have distinct functions which have the same images, and so this phi is injected. So this completes the proof that the set of real numbers is uncountable. So let us use the previous theorem, namely that the set of real numbers is uncountable, to show that in fact every open interval is uncountable. And before considering the case of general open intervals, let us consider this specific open interval, namely the set of all real numbers theta, which are strictly bigger than minus pi by 2 and strictly less than pi by 2. So let's show that this open interval is uncountable. And to do this, we will first produce a bijection from this open interval to the set of real numbers. And to produce this bijection, we will do the following construction. So imagine a semicircular arc of radius 1 with a horizontal diameter, and from the lowest point of this semicircular arc we draw a tangent line to this semicircular arc, which we think of as the real line. Now we are going to produce a bijection from this interval to r, and to do this we will imagine the theta which belongs over here as an angle which is made with this vertical radius. And if theta is positive, we take the angle towards the right, and if the theta is negative, then we take the angle towards the left. Now we see that if the point on the semicircular arc is over here at the bottommost point, then the angle is 0, but as the point slides along this semicircular arc upwards, then the angle increases all the way up till pi by 2, and if we slide on the other side, then the angle decreases all the way to minus pi by 2. Now to produce this bijection f from this interval to r, we do the following. Now if the theta is positive, then we draw a ray making this angle theta on the right hand side with this vertical radius, and wherever it hits the real line, that's our corresponding real number. So from this right angle triangle, we see that if this is 1 and this angle is theta, then this will be tan theta. And if the theta is negative but bigger than minus pi by 2, then we draw the angle towards the left and we do the same procedure. So we draw this ray, and wherever it hits the real line, that's the corresponding real number. So it will again be tan theta, but the only difference is that when theta is negative, this tan theta will be negative. So this map f is the map which sends this theta to tan theta. And let us now show that this map f is a bijection. So we want to show that it is both surjective as well as injective. Now the fact that it is surjective follows from the fact that if you have any real number, then that's the tan of some angle in between minus pi by 2 and pi by 2. Now this surjectivity of f can be proved rigorously using the intermediate value theorem, but here we simply rely on our previous knowledge of calculus that any real number is the tan of some angle in between minus pi by 2 and pi by 2. And we can also show that this function is injective. In fact, we can show that it is strictly increasing in this interval minus pi by 2 to pi by 2. And to see that it is strictly increasing, for example, we can calculate the derivative of this function f, which turns out to be 1 divided by cos theta square, and we notice that this is always positive for theta which belongs to this open interval. And so we know that this function f is strictly increasing and hence injective. So since f is surjective and injective, it is bijective, and so we have this bijection from this interval to r. So we have got a bijection from this interval to r, and now using the uncountability of r, we can show that this interval must be uncountable. So let us suppose that this interval is countable, and that means that there exists a bijection from the set of natural numbers to this interval. But then if we compose this bijection with this bijection f, then we have a bijection from the set of natural numbers to r, and that will mean that this set of real numbers is countable. But that is a contradiction because we have just shown that the set of real numbers is uncountable. So if we assume that this interval is countable, then we get a contradiction, and so this interval cannot be countable. So we have, using the uncountability of R and this bijection, we have managed to show that this interval is uncountable. So now we would like to show that every open interval is uncountable. So here of course we showed a specific open interval, namely this one is uncountable, but now we'll show that every open interval is uncountable. And we use the same idea, namely we produce a bijection from this interval which we have just seen is uncountable to AB. And for example, you can just draw this interval minus pi by 2 to pi by 2 here and draw the interval AB over here, and the bijection can be produced by just taking this point and this point and joining them by a straight line and taking this linear function which will map a theta which is in this interval to a corresponding point in this interval. Okay, and you can figure out for yourself that this linear map is the one which is given by theta being sent to a plus theta plus pi by 2 times b minus a by pi. So you see, if theta, when it is very close to minus pi by 2, then this is almost 0, so it's very close to a, right? And when theta is close to pi by 2, then this becomes pi by 2 plus pi by 2, so that's pi. That cancels against this, so you'll have b minus a plus a, which is b, so it will be close to b. Okay, so, and it's of course a linear function. Alright, so this map is, in fact, you can check for yourself, is surjective and injective, and so it's a bijection. And now we can conclude that AB is uncountable, because if it was countable, then there would be a bijection from the set of natural numbers to this interval AB, but we also have this bijection F from this interval to AB, and so there is also bijection from AB to this one, which is the inverse of this function F. So you also have this inverse mapping from AB to this interval. So you have this bijection and this bijection. Composing them, you would get a bijection from N to this interval. Okay, but that would mean that this interval is countable, but we have just seen that it's uncountable. So this is a contradiction, and this contradiction shows that our assumption that AB is countable cannot be true, so AB is uncountable. As another application of the fact that the set of real numbers is uncountable, let us now show that the set of irrational numbers is uncountable. We already know that the set of rational numbers is countable, and now we want to show that the set of irrational numbers is uncountable. Now we know that the set of rational numbers union with the set of irrational numbers is the whole set of real numbers. And one of the homework exercises is this exercise which asks you to prove that if A and B are countable sets, then their union is countable. Okay, so let's apply that exercise. Now if this were countable, if the set of irrational numbers is countable, then you would have that since the set of rational numbers union the set of irrational numbers is the whole set of real numbers, if this were countable, then countable union countable is countable, so R would be countable, which we know is false, R is uncountable. So we'll arrive at a contradiction if this is countable. So this cannot be countable. In other words, the set of irrational numbers is uncountable. Okay, so we have seen a few examples of uncountable sets, but now we can produce a whole host of new examples of uncountable sets because of this theorem due to Cantor. And this theorem says that there is no surjection between a set and its power set. So first of all, what's the power set of a set? Well, if S is a set, then the power set, denoted by this symbol, is simply the collection of all the subsets of S. Okay, and that's called the power set. So P of S is the set of all A such that A is a subset of S. So it's a collection of sets. What sets? The subsets of S. You put them all in one set, and that set is this power set. So let's consider some examples. If you take the set S to be a finite set, let's suppose that it has two elements A and B, then the power set of this set S is the set of all subsets of this set. What are the subsets of this set? Well, first of all, there's the empty set. There's also the singleton sets comprising just A or just B. and finally there's the whole set itself. Okay, and you put them all in one set. It has 4 elements, and this set with these 4 elements is the power set of this set. Of course, the set S itself can be infinite, for example the set of all natural numbers, and then the power set of n by definition is the collection of all the subsets of the set of natural numbers. Now, a corollary of this Cantor's theorem is that there is no bijection between a set and its power set, because any bijection is a surjection. So if no surjections are possible, certainly no bijections are possible either, right? And then an immediate corollary of this is that the set Pn is uncountable, because first of all it's an infinite set, right? And moreover, if it was countable, there would be a bijection from n to Pn, right? But that violates this Cantor's theorem. So since there is no bijection from n to Pn, this Pn, this infinite set, is uncountable. So in fact, if I take any countable set, its power set is uncountable by the same kind of an argument. So let's prove this Cantor's theorem, and that's the last thing that we do in this 4th chapter. So now let us show Cantor's theorem, which says that there does not exist a surjection from any set to its power set. So suppose that on the contrary that there exists a set S and there exists a surjection F from this set onto its power set. Let us define the subset of S, which is denoted by X, which is the collection of all the elements A in S, such that A does not belong to Fa. Now, does this even make sense? Let us see. If A is an element in S, if I look at F of A, that's going to be an element of the power set. So that means that this Fa is a subset of S. So you can ask the question, does A belong to Fa, or is it the case that A does not belong to Fa? If it's the case that A does not belong to Fa, then you put that A in this set, and if it's the case that A belongs to Fa, then that A is excluded from this set. Okay, so this is a well-defined set X, and this set X is a subset of S because we are only looking at elements of S and asking whether they have this property or not. So at the end of the day, it's going to be a subset of S. Now we claim that in fact this X, which is a subset of S and hence it belongs to the power set, is in fact not in the image or the range of this F. So this F, which goes from S to PS, in fact has some range, but this X, which belongs to this power set because it's a subset of S, in fact does not belong to this range. So that contradicts the fact that this is a surjection. Okay, and this contradiction shows that it cannot be the case that there exists such a surjection. So that's the plan. So we want to show that this X, which we have now constructed, is in fact not in the range of this function F. So in other words, no matter which A you take, F of that A is not this X. Okay, so this X is not the F of anything from S. Okay, so we want to prove this claim and then we would be done. So we want to show that for all A's in S, F of A is not X. So let's take an A in S and we want to show this. So if I take a A in S, then there can be only 2 cases. Either this A belongs to this X or it does not belong to this X. If A belongs to X, that means that it has this property. So that means that A is not in Fa. But now if I look at the 2 sets X and this set Fa, okay, then they can't be equal, because if they are equal, they would have exactly the same elements, but here is an element which is in X alright, but it is not in Fa. So these 2 sets are not the same, which is what we wanted to show. So we are done in this case when A belongs to X. What happens if A is not in X? Well, if A is not in X, that means that it does not have this property. That means that A belongs to Fa. Okay, now again let's look at these 2 sets, X and Fa. They can't be equal, because if they were equal, they would have exactly the same elements, but here is an element A which is in Fa alright, but it's not in X, and so this shows that these 2 sets are not the same. So again we are done, and since these were the only 2 possible cases, we have shown that this X is indeed not something in the range of this function, and so this function cannot be surjective, which is a contradiction to this, and so such a surjection just can't exist. So this proves Cantor's theorem. Okay, so we have now finished chapter 4, and in this chapter we have learned a lot of things. So let's quickly summarize some of the things that we have learned. So we learned about the standard number systems, Starting with the natural numbers, we constructed the integers, the rational numbers, and the real numbers. We also defined rigorously how their addition and multiplication are defined in each case, and also proved the standard properties like commutativity, associativity, distributivity, existence of additive, inverses, and so on. And we also learned how the order relation is defined in each of these cases, and also proved the trichotomy law in each case. In the case of the real numbers, we also learned about the least upper bound property of the real numbers, which we used in the analysis part, and we know that that plays an important role in calculus. Then we discussed irrational numbers, and we learned this useful tool called the rational zeros theorem, which allows us to deduce the irrationality of some real numbers. And we also showed in that section that the Euler's constant E is not a rational number. And then we discussed the cardinality of infinite sets. Infinite sets come in two flavors, countable or uncountable. We saw lots of examples of these. We saw that the set of natural numbers, integers, and rationals, they were all countable, and the set of real numbers was uncountable. And we proved that using the fact that if you look at the set of all sequences which are 0, 1 valued, that set of all such sequences is an uncountable set. And we use that to prove that R is uncountable, from which we deduce that in fact all open intervals are uncountable, and also the set of irrational numbers is uncountable. And then we learned about this Cantor's theorem, which tells us, for example, that the power set of the natural numbers is uncountable. Okay, so that finishes chapter 4. But now we will, in the next weeks with me, cover chapter 5. And this chapter 5 is all about this set of integers with its arithmetic operations of addition and multiplication. So we know that this is not a field in the sense that it has all the arithmetic properties, except that multiplicative inverses of non-zero integers are missing. Okay. So then such a structure is called a ring. We won't state precisely what is meant by a ring, but well, basically it's a field in which you are not guaranteed the existence of multiplicative inverses for non-zero elements. And what we are going to do is learn some familiar things but prove these along the way. So we'll start with the division algorithm. So that tells you that any integer can be divided by a non-zero integer, and then you'll get a quotient and a remainder, and we'll state this precisely and prove it. And then we will learn about divisibility and the greatest common divisor of a pair of integers, and also learn about the Euclidean algorithm, something with which you can find the greatest common divisor. And next we'll learn about the prime numbers, which are the atomic building blocks of all integers, and this very important theorem in mathematics called the fundamental theorem of arithmetic. Loosely speaking, it says that any integer can be expressed as a product of primes, essentially in a unique way, except that you can interchange the order of these prime factors. And then we will learn about something known as modular arithmetic and another ring, Zn. And over here, the equivalence relations that we learned at the beginning of the Lent term will again play an important role. And this ring will also serve as one of the examples in the last 5 weeks of Lent term, when you will learn about groups and vector spaces.